Yeah, welcome everyone for high performance computing. Today's lecture is lecture 9 on accelerators and graphical processing units. So the topic of this lecture is quite interesting because GPUs, graphical processing units or graphics processing units, have really conquered HPC in a very interesting manner. They started a little bit with some NVIDIA GPUs used for gaming initially, then people started to think, can we use them also for general purpose computing? And since then, we basically have seen a growth of GPUs and a significant impact in HPC these days, not only in system design and engineering, also basically also on all the HPC libraries that leverage HPC systems today. But before we dive into the material of lecture 9 today, let us review what we had the last time, which was about lecture 8 and the idea of how we actually can ensure that our program is running without bugs, how we can ensure we basically have the best performance. And essentially, we have learned that this is a really ongoing process all the time for application engineers in high performance computing. You see it very centrally here in the middle of the slide, where we say that essentially you would have an application, you want to measure it in order to understand what performance there really is on the HPC machine. Then you want to analyze the performance using some tool set, and you can tune, you can change the code in a manner that it better exploit the HPC system, or that, let's say, avoid some common patterns of problem in behavior and performance behavior. So you get an optimized application, but that doesn't mean you're at the end. So essentially you can measure again this optimized application, find other ways how to tune it by using these toolings. So it's an iterative cycle, as you see, and in a way you never finish, because you also have to think that application engineers also face different HPC systems, right? They face change. Here's a good example where you see in the background a blue gene architecture from IBM that actually didn't exist anymore suddenly. So application engineers have to port their application systems basically and applications to a complete different HPC system architecture. And this is of course something where then you again start with the same cycle. You have an application, you have to measure, and then basically do the performance analysis and then the tuning. Okay, but let us come to some tools. So what essentially we can firstly ensure to look and better understand the program, which is actually before you do anything on performance analysis, really. You basically have a parallel debugger here. We had the last time called Total View, and we said it's a quite nice tool, unfortunately also a commercial tool, so it costs quite something. But on the other hand, it's very powerful. It has this memory checks. It can tell you a little bit around the basically structure of an MPI program or of an OpenMP program. It has lots of tools set to really understand what is going on in the different processes that run in parallel and then at the different threads. And with this, of course, also including their variables and also the program flow. And as again, the memory is one part of it, but here for it's interesting is also maybe in MPI programs, if I have here something which works with 16 ranks, the kind of graph. So how is the communication behavior? And you see here is, for instance, one example that is highlighted that might be problematic and could run potentially to a deadlock. A deadlock was, if you remember, something when one processor is waiting for another one to finish the operation, but it is also vice versa. So basically both of them cannot anymore proceed in the kind of program flow. And of course, in OpenMP, you would have similar challenges. There we talked a little bit about race conditions. If you don't have critical regions around variables, you quickly are in race conditions around one variable that you can detect. But many more features are essentially supported when you talk about the debugger here. But also there are some free debuggers. We have also learned like Grind, Valgrind, but then these are much heavier to use because they have to be attached like the GDB debugger than really to each individual process, while here you have the parallel program as a whole to analyze. But this is really the first key ingredient. We want to have a program, an application whatever it is, what you have, a scientific application really essentially without bugs, if at all possible, right? Some principles in software engineering said there's always a bug somewhere and you cannot have 100% correct systems. However, for us in physics, when we do lots of physical formulas, when we do numerical methods based on known physical laws, we want to be sure, we want to be very exact. That's why we have also floating point, 32, and want to have really accurate double precision, maybe even sometimes. So in this way, you would say in science and engineering, we have to be more accurate. And this is meaning also, of course, thinking about debugging strategies much more carefully when putting out a paper, putting out a scientific statement about some natural phenomena that you basically are simulating, like turbulence of an aircraft or things like that. So, however, one step ahead, we have the so-called profiling, which is an interesting element, which leads us then later to performance analysis and studying what's going on. So profiling really enables us to log what's happening in an application. We see here the MPI profiling library, how it works. You have still your normal program logic, but you can link this MPI profiling library without then large source code changes. And internally, this profiling interface will then basically link back. So the key message to take away is we can here with this method basically count, for instance, simple calls of different functions. We can actually call and then basically do statistics. How many times was this and that operation called? And over time log it, of course, also with a timestamp. So in a way, we have already a little bit an overview of what basically could be put to a log file of understanding the performance later. Of course, this is something which in the current run has no impact, right? It's very important. Performance analysis often uses techniques that are actually called replay, or they look at the analysis and the performance essentially afterwards. And one of the reasons is that you usually have this trace that we had the last time, right? If you remember, the profiling is one part, but then this is maybe insufficient. We need much more event traces, what's going on in the application. So essentially the profiling interface is good and is used usually, but we go further and actually log much more details with this timestamp and then perform here and there already an automated analysis as we learned last time. Tools like Scalable are here very beneficial because they also immediately have a particular set of performance problems already identified, a particular set of performance patterns of problems, you can say, that are always coming back in the different MPI applications. So by the early analysis, which is already supported heavily by tools, not only by the instrumenter, that is basically have here a kind of augmented program that is enabling then the traces. We then have also the high-level result, which has some pattern of, let's say, non-performance behavior inside, and can also link us then exactly where that's happening. So at what time in the call path of your application, where is exactly the property, where is exactly the location in the program where this performance problem relies. We know a bit, and as a side remark, we have to remember that, of course, by doing this tracing, the performance itself of running this application at that point in time will decrease, or you have an overhead, of course, of logging everything, of tracing everything. So, but take away the message at that point in time, we're not completely interested in the cutting edge performance of the running application itself. We want to understand basically the inherent performance and the call trees. A little bit you see this with a cube analyzer, if you remember this GUI that is essentially part of Scalable. Of course, we know when we would run it without the tracing, it would be probably faster. But then, of course, we don't identify certain program constructs or patterns really that we already had the last time, like here, the late sender or late receiver as one example, which basically cover then your whole MPI program. And this gives you critical insights of really tuning of possibilities where lots of time is spent in the application, which performance problem is faced here. And of course, the key point for us as engineers and application developers is then that we know exactly where in the call tree we have been seeing this problem, and often this refers to specific use of MPI functions here in MPI wait all, for example. And then of course you see it also in the topology of the system, how it is affecting the system performance and so forth. So which processes essentially of the HPC system are affected. So in a way, using these tools, the Scalaska, it was just one example, of course. We had Vampire, if you remember, as another tool, and there are much more. Our basically today, luckily, working together with measurement infrastructure like SCORE-P. So you would say these tools also enabled these days a kind of interoperability with each other, and all of them have their unique selling proposition. So you can use even these tools in parallel to understand the behavior fully of your application. And of course, by going towards exascale computing, now we're in the petascale area, but if we are coming very soon in the exascale area, you need these tools. You need already now essentially these tools to really understand your system. But in the exascale area, we will face an enormous complexity where then, of course, we need much more tooling, automated analysis, and so forth. So that's really the main messages I wanted to leave on the table here for you for lecture 8. It's a huge area. And of course, you can think similar as we have today in lecture 9, a GPU course. There's also a lecture 8 course in centers like Barcelona, in centers like Jülich around the world, where basically you do this kind of performance analysis or scaling workshops really for 3 days, for 4 days. So of course, my lecture could merely cover just a little bit the key concepts really and some examples of tools. Of course, when you really want to engage in this, you really have to do a workshop. You have to participate in one of the scaling workshops, which would be the most beneficial way to do it, or you really have to learn and basically master these tool sets by iterative learning and constantly applying it to real application problems that really scale high. So as you could imagine, similar like I just said for lecture 8, lecture 9 is about accelerators, graphical processing units. And this is something where, for instance, Jülich, I have here some material from one of our courses in Jülich, is, for instance, just 3 days from morning till evening, nothing else. And what is a GPU? By also seeing today that we basically get many more vendors. So interestingly enough, NVIDIA was dominating the market of accelerators with the GPUs very much, but we see more and more that different vendors are actually looking at this technology. And we will also have in the course examples of AMD Instinct MI100 cards, which are now fueling emerging supercomputers like the Lumi system in Finland, where Iceland is a little bit part of, but also large US systems like Frontier. So today is really then thinking about a different way of computing as we have done in the last couple of lectures. We always were a bit focusing on multi-core CPUs. So today we will go and reiterate again what is the difference between a multi-core CPU and a many-core GPU. So these are the accelerators we look at. And of course, we want to know why that is suddenly so important. So we will see a little bit in the top 500 that it has quite an impact in HPC systems worldwide. And we have to also understand that the terminology and the architectures really that you always hear and floating around is already starting to be very complex if you just look on NVIDIA. So if AMD now is also starting, we've found again a very broad way of seeing these architectures. And basically NVIDIA was really starting with different Tesla architectures and then coming to Kepler, Pascal, Volta, Ampere systems now, which is a cutting edge today. The A100 cards, we will have some examples of. Of course, this requires a little bit an understanding also how I attach a GPU now to the host CPUs, right? So we had in the beginning of the lecture already, basically here in the HPC systems course, that there is this understanding that always a GPU needs a host CPU. And we will look on one of the largest systems in the top 500, the Summit HPC system, more in detail to understand really what a node architecture means. So basically, do you have 6 GPUs in a node, or as our Jülich system Jubels, maybe 4 GPUs per node? This is, of course, an important consideration. of the overall system architecture. And then you start thinking, what about using not one GPU, right? We would say in data sciences and workstations, people have start using this, have their workstation, maybe even under the desk, an old desktop PC, and with a GPU equipped, and then do their deep learning. But what about really using GPU at scale, using, let's say, 100, 200, and in the hundreds then of GPUs in parallel? And then we see that there are certain islands from NVIDIA, this NVLink and NV switches, that essentially just interconnect a couple of GPUs. So we cannot go, let's say, deeper. For this, we need then essentially another framework, things like Horowat and so on we will discuss. There's also another approach with GPU direct implementations. We will also review a little bit and then look and review what we have here in Iceland so far. The second part of the lecture then will be much more looking on how you actually program a GPU. So what are there in terms of programming models, what it is basically used for. And there you see essentially two different areas where we see and also have the course lectures here oriented to, as you know. There's of course data science with deep learning, where perhaps GPUs had made the biggest impact. You could also say that without GPUs, you don't want to do deep learning. You would experience this basically by exploring this in assignment 3, and then basically would look at this from the performance point of view, that running a deep learning network on a CPU for training is already very slow, but with deep learning very fast. So this is something where GPUs have a very huge impact. And then of course, when you think about really cutting edge architecture like ResNet 50, for example, to train really in a distributed manner with multiple GPUs, then this effect got multiplied. You don't want to have a multi-CPU training of your deep learning network. You want to have a multi-GPU training for your deep learning network. And there are specific frameworks like Horowat or DeepSpeed that actually enable this. And we will hear, of course, about more of this than when we have the dedicated lectures around data sciences, which are lecture 10, practical lecture 10.1 given by Gabriel Cavallaro, and also practical lecture 10.2 given by Rocco Sedona. But here, this is really the first lecture on GPUs to get a bit better an understanding what it's about. So we will also review, of course, the physical sciences, so the simulation sciences, what libraries are there. I will have a short example of SexP, which is basically then a basic linear algebra code, which is very famous, known in basically the BLAS collection really of functions. And then we will look a little bit on the trouble we have today, thinking about NVIDIA GPUs and their CUDA, which is a specific, let's say, architecture and way how to program them, which was, of course, a kind of vendor lock in the past, right? The many people have used always NVIDIA cards, so all the applications have to be using CUDA somehow. So this is, of course, one hindrance, so to speak, for the adoption. And now that people, many of them perhaps even adopted already now to CUDA because they were quite dominating the market many years now since GPUs became really on the horizon. But now we also see new vendors are coming, like the AMD Instinct, for instance, in Frontier, or as we see also the Lumi supercomputer in Finland that will actually employ also the AMD the AMD Instinct cards MI100s. So in order to do and to cope with these new vendors and the idea of having a much more heterogeneous set of accelerators and GPUs available, of course, the case can be made. Should we have not some standard programming models, right, which can deal with both, let's say, CUDA and the new AMD architecture programming models? And this is something where I have also brought you a video about AMD. They have a different, of course, idea of how to program the systems like NVIDIA. So we have to talk about some standards in the end, like OpenMP or HIP, which are actually relatively new if you compare them to MPI or OpenMP. But we also will see what we also promised in one of our lectures here in lecture 6 and practical lecture 6.1, that of course OpenMP is a little bit, let's say, oriented and has some similarities and learned and inherited some elements of OpenMP, and we will make the case toward the end of the second part of the lecture. So let us start a little bit with the learning outcomes. Of course, for you, as students, what you can get out of this is really complex aspects of parallel programming. You remember we have now MPI, you can combine it with OpenMP, then you have hybrid computing, then you basically use MPI in parallel with OpenMP. But of course, these days you have to think about, don't you want to employ or use accelerators as well? So with this, you're starting then having indirectly CUDA, perhaps in combination with MPI and OpenMP programs. So we will also learn that this is, of course, a complex setup and how you actually support this in the programming. And basically, out of this lecture, you should at least have an understanding how to program roughly these GPUs and how you can use it now as a basically different paradigm as you had before, essentially saying that the multi-core CPUs you can use now also in parallel with many core CPUs attached to it, and then essentially have very powerful applications that you can program. So let us start with the so-called term general purpose graphical processing units. And this is something which is today not really used very much. Basically, for all in HPC, everybody is talking GPUs. If you go to a conference and would say, we have so many GPUs inside our system, nobody will directly correct you and say, well, you don't have GPUs, you have GPUs, probably, because they're used for general purpose and not anymore for just graphics. But this is a term that essentially is vanishing from the practical perspective point of view. Yet, of course, from the official initial definition, it's indeed true that they, of course, use for general purpose computing. Before we go into the many core, it's also important to maybe review briefly the multi-core CPU processors. You see here a couple of them basically on a chip. We have said they are very, let's say, high in performance, very high single thread performance, really level of caches, so very powerful. However, the drawback was actually they get a lot hot and need lots of energy. So this is a very nice heartbeat. This is basically here the clock rate, right? It means how many processing it can really do. But of course, here the problem is that actually due to this heat and power limitations, we cannot grow more. Hence, the idea was, what about having hundreds, thousands of processors, but essentially not so with highly single thread performance, but let's say more moderate performance. Still, I have hell a lot of them. So this deals a little bit with the heat because they just don't have this high clock speed. In this sense, they will be not getting so much hot. So in this sense, also it was really movement of the community to go that way and the requirement to do so, because the multi-core CPU just don't really get much better. Hence, we have here a solution to this problem by using also then this many core GPUs. However, the main message to take away is really, and I will bring it again and again in this lecture, we need the host CPU still. So please don't go out in the field and say, well, we have now the GPUs, we don't need CPUs anymore. That's also wrong, right? So the CPUs are still required and it's basically still the main ingredient of a system, because otherwise you cannot do it. If it is an Intel CPU, an AMD EPIC, whatever processor there is, in the future we maybe see a European processor based from the European Processor Initiative. So this really doesn't matter, but there's still no direct technology which actually has a GPU directly as a, let's say, host device directly. In other words, you always have a very specific way how to fuel a GPU with data. You have to always go through the CPU, as we will see basically in later slides, where I also then will show you how you actually program a GPU abstractly. So this is really now these many cores, where the name comes from, where really thousands of these processors exist. You see they're not really much of cache hierarchies anymore, but a large device memory. And there's lots of different elements in this too when I come to some concrete examples later on. And also, of course, think about that. Although they have been invented for gaming, you see that, of course, it's a large market, the gaming industry with NVIDIA GeForce cards. The NVIDIA cards we have today in the supercomputers are actually quite different, and we will show a couple of examples why that is the case. So here's an example, for instance, why basically we talk about many cores. Here's a very old example on purpose to show you also the evolution of those systems. So here's a GPU that has maybe 128 cores on one single GPU chip. That's already something, but each of those cores could maybe have 8 threads. And today we have even streaming cores, which can do much more. But interesting enough, if you already compute this, you see 128 times 8 is already 1024 threads. Now, if you compare this to the OpenMP world we just had in lecture 6, this is already quite impressive, right? To pull that through, to actually work in parallel in this device. And the only bottleneck is basically that you have with these systems is essentially the bandwidth. You have essentially here from the main memory to the device memory. You always have to go via this link actually to fill the GPU. And this is perhaps today the biggest problem we have in scientific computing. Otherwise, the acceleration here works quite well with massive parallelization today. And essentially, they're really doing a lot of similar work, but of course, then in the order of thousands. And this enables us for many applications to leverage this behavior in parallel very much. One of the good examples is deep learning. We will see that in lecture 10, in lecture 11, or lecture 10 and practical lecture 10.1 and practical lecture 10.2, where we really learn about that deep learning is nothing else than matrix vector and matrix-matrix multiplications iteratively again and again through a big neural network here, so-called tensors. And basically, you see here, this can be done independently from the color coding. You remember this in one of our earlier lectures. We said this independent computing, as you see here, in order to have this matrix multiplied with this vector here, I can do this nicely in parallel without ever knowing what's in the other cells here. All I need to know is my specific color and I'm done. And in the order of magnitude, right, in scale, we would do the same to fuel a GPU, and all of these 1,000 threads can work on these different colors of a very large matrix, maybe even 3D, and so on. And this gives us opportunities in science. And one of them is here, for instance, just an example shown that it's not only in gaming, it's basically the AMBER package, which is quite a very strong package for molecular dynamics. Basically a very specific field in HPC. You will learn also in one of our application lectures coming later. And you see here some of the generations really then to the Kepler architectures here of GPUs. And here you see the performance, and you can basically see that over the time coming then to the Pascal architectures here, of course with different basically varieties. The P100 was quite often used and is strong, but today we have mostly V100 systems. And as I was alluding to, the Ampere architecture, which is brand new, essentially is now basically also coming and even beating the performance of the V100s. This is just a benchmark here, this myoglobin with having 2,492 atoms on basically this different GPU architectures. But it shows you that, of course, this is a big, large impact now also on all the scientific packages we have in HPC, in the simulation sciences. Many of those have been ported to now actually use also GPUs. You have to think about that 15 years ago, 10 years ago, maybe, people were not thinking that way. The most people were thinking, and engineers and application developers, we have MPI and OpenMP. So most of the codes have been in scientific computing along these lines. And now essentially it's for the first time that we really have to think about there's a change, there's a different way of programming it than if we essentially start here with this idea of using really GPUs to accelerate certain parts of the problem or certain parts of your application. Right, so when I think about now what generations I could show you, of course you would think I show you a very old one here, Fermi, for one specific reason, but also you have to think about that this was really an idea of, let's say, evolution. So you see here, let's say this many core system started relatively small. So of course there were a couple of sockets, and depending on the sockets of the host CPU, you attach then also essentially GPUs alongside. And you see here that the CUDA core is a very specific idea of how you create it. It's not a typical core that you would have a CPU, of course. It's a many core architecture, completely different. And the interesting thing is now that over the years, there came more and more architectures, and performance improved. And we see it was really a long way to come this far. So we had really Kepler architectures, Maxwell, Pascal, Volta, then really prominently here already, and then really more cutting edges now the NVIDIA A100 Ampere architecture with specific tensor cores. So in the beginning, there were so-called CUDA cores, and of course, people were thinking about deep learning, of working with tensors, which are actually nothing else than multidimensional arrays. But of course, there was not a really specialization on this. Today, these tensor cores, we will see in a moment, are really specialized for certain workflows and for certain basically parts of your application. And of course, they don't have a couple of hundreds of cores anymore. They now having streaming cores, very specific cores in the thousands. And the impact of these evolution hops, if you want, is really interesting shown. And it also shows you how big impact still the memory puts on the perspective, right? So you would see, like, here's the Volta 100, still cutting edge today. There's a floating point 16, so not really 32, so half floating point performance here. So, but still the interesting thing is you get A100, the new architecture, which is already much better, but depending on the, let's say, throughput of the memory with 80 gigabytes here, you essentially can then see that this plays a huge role essentially to really train then deep learning models. So this is, of course, just one specific workload. For other workloads, I would refer here to this white paper, which is quite interesting about the A100, how it is also used in different fields. But this is an important way to understanding this scientific innovation just don't pop up at once. You see here the Tesla architectures and improved suddenly over time and really made it then to market dominance, where we see, of course, and also the AMD Radeon CPUs, GPUs at some point in time catching up, but really can come closer to the P100, V100, and now the A100 is even much more here. This is a double precision sketch, but it basically is also very similar when you think about the single precision. So this Interseon architecture was quite promising and at some point in time, because also here was one of the ideas that we maybe find a GPU or an accelerator, more accurately speaking, that actually can act as a host CPU as well, right? So slowly repeating. The accelerator here would be at the same time also directly a host CPU, so you wouldn't have that problem of saying you have always this device memory and then this host memory, and of course it would be still hard to program, but in a way that would be really, let's say, a help. But actually it was stopped by Intel, this development angle. And what we really see here today in the top 500 list is by far the dominance of NVIDIA. I think there's no surprise in this. The only vendor, let's say, in the last 10 years that by far has created this GPUs to a maximum degree and is, of course, incorporated in most of the systems today. Here you see our Jülich systems already presenting the modular supercomputer. In our booster module, you find, for instance, 4 times NVIDIA A100 cards per node. And of course, this system would have not one node, it would have 936 compute nodes times 4 GPU nodes, and then you should be arriving roughly at 3,700 GPUs. So these are all, of course, now available, not basically only for one user. It's a multi-user system, if you remember, but still a very powerful system and can be used with quite significant applications. I should mention also the Summit architecture a bit, which is also using essentially many nodes. And of course, in each of the nodes is even 6 NVIDIA Tesla V100 GPUs. So that's also impressive. If you think about that, basically one card already costs a lot from this V100. And if you have 6 times number of 4,608 nodes, you can imagine that this is essentially around 30,000 GPUs that have to be financed. And of course, this is something which is perhaps one of the most expensive systems in the world. So not everybody can essentially do this. This is a status of November 2019 still, but the architecture is basically here illustrated in a way showing you a little bit what we mean with these NV links, right? So the NV links is a specific interconnect between the different GPUs in order to also actually have a very nice interconnect between the GPUs. You have the high bandwidth memory here, which is basically the device memory, but we have also the CPUs and the memory that we have here in the host CPUs attached to them, right? Which are basically then enables us to using here the NV link many different of these GPUs then in parallel. However, the NV link here in this version 2 fully interconnects the 3 GPUs, but we see also that when we want to scale to the many GPUs we have just read about, then this is of course not so simple. Now thinking about the idea of essentially HBM2, which is very important, and thinking about where the bottleneck is today, we have really a very high memory bandwidth from the accelerator to this HBM. This is very good, so host memory and the accelerator. And of course, our memory bandwidth is also okay if you consider the DDR and CPU, but still connecting then essentially the CPU and the accelerator is sometimes really restricting some of the bandwidth. And of course, this is a hindrance if you want to have to think about that accelerators are mostly used for data intensive problems here and there. To really fuel the accelerator with more data, you're in trouble. However, HBM is there and enables a higher bandwidth really than normal, let's say, DDR RAMs that you have there. So that's already helping a lot to make essentially this data throughput that you need for accelerator really catching up. Still fueling, then you need a really good strategy to really bring into the device memory always the data that you want to compute. And there's lots of work, of course, in this area driven by, for instance, JEDEC here, which is a global leader for standards in this area. And HBM is also then essentially used in other areas, or other vendors like AMD is using also HBM technology, which is quite interesting. And something to think about, that this is really a very powerful part of the system. You see here a couple of more examples. The NVIDIA Tesla Volta V100, for instance, just as an example, nicely illustrated with this new Tensor cores. These are very basically with mixed precision, with floating point 16 versus floating point 32, because in deep learning you will have often the fact that you don't need this double precision, this perfect accuracy. You can really basically see that for deep learning, it is okay to have just floating point 16 here and there because it has a regularization effect, something that's not clear to you and obvious. We see how that materializes when you have lecture 10, right, or practical lecture 10.1 and 10.2. But here, this is a really impressive idea that these tensor cores are really optimized for these workloads, while at the same time have more mixed precision strategy for matrix multiplication and accumulation of calculations, and so can be much more faster than basically having a totally, of course, double precision computing performed. So more on this also in the practical lectures 10.1 by Gabriel Cavallaro, for instance, and you see really this compared to Kepler architectures, Pascal architectures, now the Voltas is really breaking down the deep learning training really significantly already, what used to take a lot of time before. So understanding the interconnects again from GPUs, the NVLinks and the switch islands is now the similar strategy. So it has this NVLinks. Of course, this is one part of the game why it's so fast when you want to interconnect these GPUs. Then you would have also the idea of this NV switches that are essentially multiple of those NV links. And to really provide this all-to-all GPU communication, you see a little bit here. But also this is limited, so you cannot really, that's why we call it islands. You cannot have basically a whole system, right, interconnected in that way, like a summit system. It has parts of it, of course, as NVLink and as we switch on a more node basis, and basically this idea is not scaling up very well. So that's why also in one of our applications and projects we have in this area is working on these solutions, basically using a different technology that you have heard here in the DEEP project already, modular supercomputing. And when we look there a little bit on this booster where you have seen the Juval system, right? It's one idea of an extreme scale booster that is already implemented. There are also ideas of how to really, you could essentially scale up with then so-called GPU direct implementations. So this is a different strategy than what you think about this NVLink and NV switch directly. Instead, here you would say that you essentially use here this conventional strategy. How you would do it, you would have a computing with a CPU, you would offload data, essentially use it as an accelerator with a so-called kernel we'll see in part 2 of this lecture series, then return to your MPI and use basically then other nodes. And then in your own node, you would again, always go then with the data through the host CPU to communicate it away. With the GPU direct implementation, there's a possibility to essentially send the results out of the kernel, basically then directly through the node, and essentially assessing then other nodes. And this is an opportunity to really scale up and essentially then also to use the CPU if you want, not anymore really for computing, but more as a network interface, so to speak, and compute the most aspects in the kernel. And with this maybe come to much more homogeneous workload and so scaling better. So these are methods and ideas, also what we pursue in GPIST. Here in the dump prototype, which is available as assignment 3, there would be essentially this NVIDIA V100 cards available for you to play and to really test a little bit deep learning. And essentially, you will see that here, this is an interesting system to work in. Of course, it's a very relatively low amount of GPUs here available because it's not considered also for large scaling like the extreme scale booster here. But here the idea is rather supporting with large memory, for instance, also the idea of analytics stacks like Apache Spark, elements we do in the cloud course, for example. So then when we think about Iceland, do we have GPUs? Yes, we also get more of them. In the moment you see we have quite old GPUs here, 3 nodes, and also one V100, very cutting edge node that you see basically per node. But we also got a new upgrade on the system, which is not anymore GAPR. So basically we see soon a new system in Iceland that will appear, which has more GPUs. And we are also in the process of applying for more right now. Then, of course, we also have to think about that Iceland is part of the LUMI consortium, right, of the supercomputer in Finland. I will talk about a bit later on again. And then basically we see that there are actually GPUs, but they are the AMD Instinct MI100s, which is also quite interesting. So you have different technologies and different HPC systems. At the end of this lecture, I would like to give you a very minimum demonstration with this interesting video, which has a visual impact, I think, explaining directly what a CPU does and what a GPU achieves by using and leveraging, let's say, maybe not the most smartest cores, but many of them in parallel. And of course, I'm not financed by NVIDIA. I'm just having to say they have good videos to show the substance here of GPUs in action.
All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo 2.0.
When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10,
9, 8,
7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
All right, that's really all I have for the first part of the lecture. Again, take away the message, we could talk about this much more longer. It would be requiring at least a 3 to 4 days tutorial and training from morning till evening to really understand the full capabilities of GPUs, the architectures of GPUs. We didn't handle so much the different ingredients there. But in a way, you have now the basics of what GPUs are and actually how you can compare them to the multi-core CPUs you already know. And we will continue with the second part, essentially then looking more at libraries and programming models after a short break.